So yeah, I want to talk about sort of learning language by grounding language today. And so maybe before I get into sort of how I think we can ground language in machines and computers, I want to talk a little bit about sort of language learning in general and why I think that grounding language learning is something that we should bear in mind when we look at NLP models. So I think you've done a couple of talks on language already in the summer school so far. And when you think about sort of how do machines learn language, there's different ways we can try to teach language to computers. And so the different ways are mostly a function of the different types of data we use for that. So you can look at things like labeled data, say sentiment analysis, where you have thousands of movie reviews, and some of them are labeled as positive, some are labeled as negative. And based on that, we can train a system to discover sort of whether something else based on the text is a positive or negative story. Or you can have just huge language corpora, the kind of things you use for machine translation, where you just have tons of parallel text and tons of text just in a single language, and you learn statistics over these kind of things to then learn sort of how do you map language from one language into another. And then there's other things, it's like parse trees and knowledge graphs, the kind of information you get on Freebase or on Wikidata that you can use for then question answering type problems, or sort of the kind of knowledge graph completion work, image and text pairs that you can then use for, again, image classification, given text labels, or caption generation work, which has been quite popular for a number of years. So of these things where you have an image and you generate a caption for it, which again just happens by looking at loads of images and matching captions. And this, I think this is sort of, it's not exhaustive, but it's sort of a reasonably broad idea of how we think about language learning machines and the kind of data we use for that. And then the question is sort of what do humans do? And so this is what humans do. And this is me failing at sort of trying to compress the whole degree in linguistics into a single slide. So, starting with the guy in the top left, Skinner, he sort of started off with his behaviorist theory saying, children learn language through reinforcement and imitation. They learn language by saying things, and then they look at the feedback they get, and if the feedback is positive, they're like, okay, maybe what I said was a good thing. If the feedback is negative, they won't say that again, they'll do something else. So, like language learning by trial and error. And then the next guy up here, Chomsky, basically said Skinner is wrong. Actually, if you look at the poverty of stimulus, the little amount of language that children are experiencing in their sort of education, their upbringing, reinforcement learning isn't going to cut it. There has to be something else. There has to be some sort of innate ability in humans to learn language. And then come along sort of Catherine Snow and Jerome Bruner. They say, actually, no, both of these people are wrong. It's all about the social interactionist model, and you acquire language sort of in the context of parent-child interaction, all of the other things that happen within that sort of framework of interaction. And it continues like this, right? And come along next to people, and they say, actually, all of you people are wrong. You acquire language through sort of these cognitive processes in the brain and competition of different signals being processed at the same time. And then next person comes along, Piaget, and says, well, actually, it's a bit different again. Like development is sort of these 4 different stages, and at some point you develop symbolic reasoning, and then language only happens once you figure out symbolic reasoning, so it's just this extra layer on top of that, and so on and so forth. And I think that there's 2 conclusions you can draw from this slide. One is nobody knows how we learn language because they all disagree with each other. And the second conclusion we can draw from this is sort of, this here. Like humans learn language by inferring statistics from a billion tokens worth of text. Nobody has ever suggested as a plausible theory of language learning. And this is kind of important, right? Because when we think about computers, this is how they learn language. When we think about humans, this is definitely not how they learn language. And so the question is this a problem or not? You could say, well, actually, it's not really a problem because the machines are doing just fine. Most NLP systems today are trained on just a ton of text data. And, when you look around there, actually, we're doing fine, right? There's been loads of large progress in machine translation. There's been amazing progress in question answering over the last couple of years, language modeling, information retrieval, you name it. We're doing just fine. So maybe this sort of anachronistic approach isn't so bad after all. But actually, you could also say, no, problem, because it doesn't work. So think of like a really simple example sentence, like a young woman in front of an old man. And now if I'm going to ask you sort of which of the next 4 sentences is the most similar in meaning, a young man in front of an old woman in front of a young man, a young woman behind an old man, or an old man behind a young woman. I think we'll sort of get consensus, but let's try that. So who thinks the last one is the most similar? Okay. Who thinks any of the others are the most similar? Okay. So let's just say the consensus view is all humans say this. Right? The young woman in front of an old man behind a young woman means kind of the same thing. But there was this interesting paper by Gershman and Tenenbaum a few years ago where they took all sorts of language models, pre-trained word vectors, these kind of models that try to learn a representation of a sentence, and then see, what does the computer think? And so you take a matrix vector, recurrent neural network with a bilinear regression on top of it, and it says this guy here. That's not ideal. You try a different kind of similarity measure, you get this guy. Take different word embeddings, you get these guys, those guys, those guys. Basically, they've tried a ton of different ways to compute vectors for sentences, and across all of these things, they got all sorts of results except for the one that we're looking for in terms of semantic similarity. And that's not great, right? I mean, this is fine for a lot of things, but if you want to get language understanding into computer, this is bad. This is not understanding. So why is that? Why do humans and machines disagree on this problem? And I think the explanation is quite simple. If you think of the sentence, a young woman in front of an old man, all of you can picture the scene, and it looks a little bit like this, right? Young woman, old man in front of each other. And then you try the other sentences, you can picture the matching scenes, and you'll see, the young woman in front of the old man behind the young woman. That sort of gives you the same scene. That gives you the kind of same grounding in reality, the same kind of idea of what's happening in that scene. So you can say, okay, these two things describe the same thing. Whereas when you feed this into a word vector composition model, what they see is all of these words. It's just a surface form. And then when you look at sort of the similarity just in terms of pure surface form, in terms of words, I sort of highlighted and read the words that are different compared with the base sentence. You'll see, this guy here, an old man behind a young woman, is semantically equivalent, but on the pure surface form, the most different of the four candidates. And this sort of, suggests both why the computer fails to solve this incorrectly, as well as possibly what's wrong with sort of our idea of how we encode language in computers, and how this might not lead to understanding, but just to something else that is much more closely linked to, surface form statistics. Which are fine for most problems, but when you talk about language understanding, of course, you fall short. So how can we fix this? And why do I sort of focus so much on this one thing? This is just one problem. This is just sort of one nice example for this. Of course, there are many other things that are really difficult for machines to learn. So there's spatial reasoning, the kind of example from just now, and anything about relative size. Try to teach a computer about relative size. This is crazy difficult. Resolving ambiguity, coherence in longer bits of text or in dialogue. All of these things are really, really difficult problems that these days we struggle with getting models to learn how to pick these things up properly. And I guess this talk is sort of about this argument that maybe grounding language learning in other types of information should allow us to learn better semantics. So by removing language learning from this model where we just have a lot of text that we learn statistics over, and instead we look at language learning in the context of something more than just text, then maybe we can sort of work towards building models and developing algorithms that can solve some of these problems along the way. So let's see. I'm going to start with sort of this specific failure case I described just now. So Gershman and Tenenbaum, their work was on, sorry. Fair question. So with grounding language, I basically mean anything where you don't look at language, at text in isolation, but you look at text in combination with other modalities. This could be you have text and visual information, you could have text and action, you could have text and video, text and sound. You could see text in the context of something else happening. That's what I mean with grounding. So basically there's a modality beyond words. Yes, basically. yeah, fusing different types of data and also maybe different ways of learning on that data, between sort of just a passive looking at data and active sort of interacting with data. But yes, so for this specific problem, this spatial reference problem, the old man behind the young woman, this Gershman-Tenbaum paper, this was about identifying this problem and showing that sort of conventional language learning methods fail at this. And so I've done some work on this with colleagues where we kind of try to do the opposite, as in sort of taking the problem for granted, trying to find a way to solve this. And so to do this, we built this large corpus of 3D scenes. So you have this sort of gray room in which we place a couple of random shapes and objects. And then you can sort of look around the room from different viewpoints. And we have a script that generated synthetic descriptions for what you see at a particular point. So, for instance, here, number 1, the synthetic description is something like, there's a pink torus behind a lime icosahedron. And on top of that, for like a smaller subset of the data, we also got natural language descriptions from Turcos, and we showed the image and asked them to describe what they're seeing there, sort of in a way that would allow someone else to basically paint the scene, draw that image again. What should I do? Sorry. We'll get there. Is this better? Yeah? Okay. So we have these different descriptions, synthetic and natural language. And now for each scene, you have to think of a scene as two parts. One is sort of the 3D model of here's a room, here's the different things inside that room. And then the second, individual images from different perspectives of that image. So just a snapshot. This is sort of what you see when you stand here. This is the description someone would give for that. And the idea behind building this data set was that then we can train a model that learns sort of both the language and the visual information in some kind of joint manner. And so the model we came up with is this sort of bimodal encoder-decoder setup. I'll gloss over the details a little bit here. We can talk about this more if you're interested. But the main idea here is really that so you have this representation network that takes multiple snapshots of a single scene, so from different camera angles, and then it encodes the text together with the camera angle into sort of a camera angle specific representation, and then fuses these guys into a scene representation. The idea here being that the scene representation then should be independent of the camera angle, should sort of capture the whole 3D image, the 3D composition, rather than just the individual views on it. And so this is all text, and then what we do with the scene representation is we feed this into a generation network, which is sort of based on top of a variational autoencoder that sort of gets fed both the latent image, a query, which is the camera location, and the scene representation. And I mean, the mechanics don't massively matter. The key idea is sort of that you have this KL term between the latent and the renderer network, which is a loss that basically punishes using information from this autoencoder. And that sort of encourages the scene representation up here to convey as much information as possible so that over time you can stop using the autoencoder and you're able to generate these images just from the textual description. All of this is not super important, but the super important part here is that now we have something that learns language, learns to read language, learns to convert language into a vector representation to something that we can do math with, whilst grounding that language, if you so want, in the visual imagery of a scene. And actually going beyond, it's not just grounding in a single image, but it's grounding in sort of this whole 3D scene. So you're grounding something in sort of a 3D scene. And that was the hope, would encourage the model to learn to understand spatial relations. So given that, given a trained model, we kind of repeated the experiment I described earlier. So we constructed the base scene, and then these 4 changes. The adjective change, make the woman old, the man young. Noun change, woman becomes man and vice versa. Preposition change, in front becomes behind. And finally, this sort of invariant meaning-preserving change, where the woman in front of the man becomes the man behind the woman. So you leave everything as it is, you just change the order in which you talk about the 2 objects in a scene. And of course, you can do this with sort of our synthetic data set, replacing the people in this here with our geometric objects. And then from that, you get the synthetic descriptions, which match the ones from the Gershwin-Tenbaum experiment. We can rerun exactly that setup and see, does our model do better than all of these other things? And it does, much better. Awesome. So this is the human ranking. So here's sort of the base scene, the comparison, and this is the ranking where people were asked, how similar is this sentence to that sentence? And of course, people said the meaning invariant one was the most similar. And then they have this slightly strange ranking where they say, well, if you just switch the two objects around but keep them in the same room, that's sort of similar still. If you change their age, if you change the adjectives, that's a bit less similar, but still better than if you change the nouns around. So this is the human ranking, and the ranking that we get is similar in the sense that the meaning-preserving one is by far the most similar according to our model. So feeding in the young woman in front of the old man and the old man behind the young woman is the most similar representation that the model will spit out compared to all of the other ones. We don't get the rest of the ranking right. I don't think that matters. We get the key bit right, which is the thing that means the same, the thing that is grounded in the same reality gets the same representation. So this is nice, and I think this is sort of like a nice motivation why, grounding language in something else can help with specific problems. So, this is a reasonably specific case, of course, where we say, well, we have language and we want to ground it in something that allows us to learn spatial relations. So let's ground it in something that uses a lot of spatial information and where spatial information is really essential to solving the original learning task. And then as a side effect, we get embeddings that represent sort of these invariances correctly. To give you a bit more of an idea of sort of what the model looks like, so this fully trained model, you can then use to sort of encode your text and try to generate scenes from it, try to generate images from it. And this is what it looks like with the synthetic language, and this was the natural language. And I've put sort of one bit of ground truth here. So this is kind of the scene we started off with. This is the same camera angle. So they look pretty similar. And then we just rotate the camera angle around. And what you should see is that there's consistency in the placement of the objects relative to each other. It's not perfect, it's not pixel perfect, because of course that information you don't have in the text. If you say there's a green box next to a red circle, they could be anywhere next to each other, right? But you do get this consistency, which is a really nice effect, and sort of shows that the model really learned how to place these things relative to each other, how to interpret spatial relations correctly. And yeah, as I said, we did this for both for synthetic language and natural language. Like this sort of very formal experiment with the young woman, the old man. Of course, that's pretty synthetic language. But the nice thing is it also works for natural language, which is a lot more vague and a lot more varied. So this is sort of an experiment where you then, given the text, you generate a scene, have this image, and then ask human annotators, does this match the description? Is this sort of what you imagine you should get when you see this text? And this works reasonably, like it works very well for synthetic language and reasonably okay for natural language, which is, a tiny data set because, well, we had to pay to get people to write these things for us. Anyway, so this is kind of a really long-winded motivation for why I think grounded language learning is interesting. And so to give an example of like one concrete thing that most machine learning NLP models will fail at, but that you can fix by grounding language in another modality. Of course, if you want to go beyond this, there's sort of this question, can we do language grounding in a more general fashion? Can we sort of do this more properly? And I think if you want to go beyond this, then you end up running into this paradigm problem of trying to figure out what is the sort of minimally adequate training paradigm for an intelligent agent to learn to understand language. And so, as I said, the previous model, that was a nice start. We integrated language and vision and location information here, sort of the camera angle. But there was no action. This was just a model sort of receiving data, spitting out data. It couldn't interact with the world. It couldn't modify the world. And I think for sort of an agent to really be able to learn language and learn the meaning of language in the context of the world, in the same way that we understand language, you need an environment where linguistic symbols are sort of grounded in that environment. whilst having agents that can act and learn in that same environment. Now, the problem, of course, is then, all approaches to natural language understanding so far have failed, except what us here, humanity, we're kind of good at this. Everything else, awful. And so the question is, what's sort of the data environment in which humans learn language? Because that seems like a good starting point when we try to figure out how to do this for computers. And if you think back to the linguistics slide from the beginning of the talk, nobody has the answer to that. We don't really know. I mean, like there will be a lot of answers, but they all contradict each other. So that's not massively helpful. But there are a couple of things we know and we can all agree on. For instance, like children learn language with minimal direct teaching, with incredible variations in data. They learn amazingly quickly from super sparse and super ambiguous data. And finally, children can learn language in crazy adverse circumstances. You can learn language despite blindness, brain injury, without the ability to move or even to speak. Children can learn language in all of these setups. And that sort of suggests that, however we do learn language is a really, really cool mechanism. And this is probably something worth investigating to see if we can imbue our models with aspects of that to get some of these properties right in our artificial agents too. So this thing that we sort of started with as an attempt to get towards that is this 3D environment where you can have billions of different synthetically generated tasks. They're all sort of language driven, so you have the grounding in the form that sort of the agent is given language, given a particular action to execute, and then it acts in the world, has to sort of explore, search for things, pick things up, learn to identify objects by shapes, by colors, and so forth. And the idea was that this could be sort of a decent starting point for seeing if we can train agents to learn language in here. Maybe we can learn a little bit more about how they learn language in such an environment and see if we can scale it up further beyond that. And so the environment we use for this is called the DeepMind Lab environment. It's basically what you saw in the video before. And so you have these three kind of input streams, a reward signal, pixels, which shows you what you see, and language in our case to give you things to do. And then there's sort of a bunch of actions, pretty much like any sort of ego shooter game, except we removed the firing action when we modified the original code for this. And this is something that's been published, so you can download this and play with this yourself and try to train agents in this kind of environment. In terms of the language in there, this is like reasonably narrow. There's sort of 40 different shapes, a bunch of different colors, patterns, shades, and sizes. So there's all sorts of ways you can describe and reference objects and the rooms you're in order to come up with sort of tasks that force the agent to perform certain bits of understanding. So that's sort of the basic environment. And keeping it basic, so here's kind of the simple agent that we started with in this environment. So this is built on top of that thing that learns to play 2D games. Maybe some of you have seen this paper that DeepMind had before my time about sort of learning how to play Atari games. This is basically all it was, which is not crazy complicated. You get visual input, have a convolutional neural network that processes the pixels into a smaller representation. Then you have a recurrent neural network on top of there with an LSTM core, and out comes an action and a value function, and that's it, right? And none of this is new, by the way. So I mean, convolutional networks, that's Jan LeCun, 1988. LSTMs is Hochreiter, 97. Recurrent networks, Hermann, even earlier, and reinforcement learning, Williams in 1992. So there's no magic in here. And sticking to the theme of no magic, now this thing can understand language too. We have a second input stream with language, an extra LSTM that processes language information, and then a little mixing module that merges the visual and the language information post-processing. In practice, concatenation is a great mixing module for these sort of things, but don't tell anyone. And that's the thing that we used to see if we can use this sort of grounded environment, if you so want, to learn how to train agents to learn language. So starting with something really easy, like a simple test case, the single words. So here the agent is being told, find a pencil, it picks up a pencil, toothbrush, gets someone right too, and so on. This isn't crazy complicated. On a video, it kind of still took a surprising long time to learn, just because at the end of the process the agent has to go through, moving from the back of the room to one of these objects, that will still be 100 actions, moving left and right and forward. And then at some point figuring out, okay, I picked this thing up, now I get a reward, why was that? And, 5 weeks later, oh, maybe it was because of the language, maybe there's a link. But the good thing is it works. Simple agent, simple task, grounding, done, boom. Coming in? What? Oh, the hexagons here? Yeah. I think that's just a pattern. The agent is a bit more continuous than that on here. I can't tell you exactly how continuous, but I think on average this sort of a trained agent came down to 60 actions from start to picking up an object. Now, as I said, learning is crazy slow, but the good thing is there's all sorts of auxiliary objective functions you can stick into these agents to make learning a bit more plausible. So, going back to linguistics earlier, Skinner's saying, you learn language through reinforcement, you say something, and you get sort of sugar or a slap on the back. That's sort of this guy. It takes an awful long time. But what we can do is sort of imbue this agent with a bunch of auxiliary objectives that speed up the learning and speed up sort of the agent in figuring out that there is a link between the language and what's happening in the world, and these two things plus my actions link to reward later on in life. And I'm not going to go into too much detail here, and again, this is published. If you want to see the math, I try to keep this talk formula free. Sorry.
Do you know how many training cycles are spent learning the game of picking objects versus learning a vocabulary? So maybe if you...
4 slides. Yes. So, but yeah, with the auxiliary objectives, there are a couple of reasonably simple ones. So there's reward prediction, value replay, which is basically agent sort of looking at what it's done in the history, trying to learn classifiers over did this sequence of actions and inputs lead to me getting a reward or not. There's sort of this temporal autoencoding where you try to predict, okay, if I move forward now, what will the world look like? If I turn left now, sort of what do I imagine the world to look like? Which is basically just the agents of learning basic motor skills, trying to figure out sort of the consequence of its immediate actions. And then there's language prediction here, which is kind of neat because, so here the idea was given a sequence of inputs, if you see what the agent did, can the agent after a while guess what the language instruction was that led it to do such a thing? And this is kind of neat both because it helps learning and also because sort of it gives us some form of interpretability, as in we can look at the agent and see what does it think made him go towards that key. And now, it was predicting it was told to either pick something purple or key, brown or cow. Actually, it's pretty decided this must be a cow. I'm going here because I want to pick up a cow. And in the beginning, it doesn't know, and now it's looking at this thing and sort of, again, switches through all kinds of possible instructions that would cause it to pick up this hat. Yeah, so back to your question, maybe you noticed on the previous slide, even with all of these auxiliary objectives, this is 500,000 training iterations. And this talk is sort of in the context of can we get computers to learn grounded language so they're a bit more like humans in their language learning. And I promise you, nobody has to hear 500,000 words to learn their first word. That's just insane. And nobody has to sort of, say 500,000 things until the right thing comes out. So this is crazy slow, which is unfortunate. But there's some good news in there, and I think this is what you asked, is that learning gets faster over time. So once you know a couple of words, learning gets a lot easier. So if you compare these 3 agents, so this is an agent that we trained from scratch. This is an agent that we already trained sort of to learn 2 different words in a different setup. And this is an agent that learned 20 words already. And all 3 of them are thrown into a new game where they encounter 20 new objects and have to learn 20 words and sort of to solve this thing correctly. And if you compare, like this agent takes a long time until any learning happens, and then this guy gets there a bit faster, and the one that already has 20 gets there even faster. And this is the slide where the linguists in the room sort of shout abuse at me, but it looks a tiny little bit like human learning. Like there's sort of this idea of the vocabulary spurt, where sort of, human children, they need a long time to figure out all sorts of other things in life. In our case, edge detectors in a ConvNet. In the baby's case, probably something slightly different. But this is sort of that thing, and then there's sort of conceptual bootstrapping, which is the idea that the more things you know, the easier it is to sort of understand a new concept. Like, if you know what a car is and what an airplane is and what a boat is, it's really easy to explain to you what a hovercraft is. If you don't know any of these things to start with, then we're going to have a really long conversation to get this across to you. And I think this is sort of what you could argue is happening here. So, going away from these single words, you can do the same thing with slightly, longer sequences. It's not quite sentences, but bigrams, trigrams, that kind of stuff. And the agent still learns to do these things correctly. Now, of course, there's a bit of compositionality in here in the sense that, like a green toothbrush will just be one of the two objects, even if the other thing is green or a toothbrush. So it needs to learn to incorporate both bits of information. And this is nice because it allows you to test for other things. Sorry, I can't hear you.
Did it confuse brush with toothbrush or something?
Oh, to be honest, this was just the way that the items came in the environment. I never thought of separating the two things out.
Okay.
We probably should have done that. But yeah, so the nice thing is you can test for other things here, right? And so one sort of interesting thing that we keep trying to get right in language learning is compositionality. And the nice thing is these agents have seemed to naturally generalize word composition. So say if you train on a bunch of unigrams, individual words, and then just a couple of different bigrams, then you get this sort of blue learning curve. And then if you take that trained agent and throw it into a new level where it encounters new bigrams that it has never seen before, it will still get those right. So it will sort of be able to understand how to compose two things together, even if it's never seen that thing before. So like this agent would have never before seen a pink ladder, but it will have learned sort of both the concept of what is a ladder and what does it mean for something to be pink sufficiently to solve this correctly when presented with a task to pick a pink ladder. And you can even go one step further, and this sort of goes to like decomposition and recomposition. So if we just train on bigrams and then test on new bigrams that you haven't seen but you've seen the constituent parts, it will still get this right. Again, sort of with hardly any gap between the training and the test results. So I think this is kind of nice because language understanding, this is not. Some degree of being able to handle composition, this is. And considering how simple the agent was that I showed you at the beginning of this, I think that's sort of a pretty cool result. So how far can you go with this guy? All of these things were a simple small room of varying sizes with a varying number of objects in there, but can we go sort of slightly bigger if you search and explore kind of things? Well, no, that's not a good learning curve. But then what you can do is sort of build curriculums around these things. So, start off in something much simpler and you get an agent that learns. Then you go to something a little bit harder and a new agent will sort of struggle to get there, but the agent that's already learned the simpler tasks will get there almost instantly. And this sort of continues as you scale up the vocabulary, as you scale up the size of the rooms, until you get sort of to the final thing that we tried. And you can't learn it directly. I can't, maybe you can with a better algorithm. I can't, I really tried. But with a curriculum, you can. And again, this is sort of nice, not just for solving this task, because quite frankly, in the real world, nobody cares about agents walking around in labyrinths, picking up green ladders. But it's nice in the sense that it shows you that the way the agent learns sort of to understand the world and to interact with the world is transferable in some sense, in the sense that sort of the understanding of objects, of shapes, of colors transfers to different environments. It's not just grounded in sort of one specific set of actions. So this is what the guy looks like in the end with sort of a more complicated setup. It's like pick the green thing next to the red thing. There was a green thing, but the other thing was not green. It runs around a bit more. Here's a red thing. There's a green thing. Hooray! It picks the green thing. And, well, again, sort of going back to where we started, the interesting question is, does this actually tell us anything, this model? Like, is there anything in this model that we can use, that we can learn from this model to see if there's any link between this and human language learning? Is there anything we can take from the kind of learning we do with these sort of models that we can apply to other language tasks, other kind of more applied tasks where we actually care about this language understanding in a serious way? And so one nice thing is with these kind of machines, when you sort of try to start looking at this from the perspective of human language learning, we can sort of look at different kind of phenomena you observe in humans and see if they also apply to the machine and sort of whether they manifest themselves in these models and how. So there's one really cool human language quirk that I really like, which is shape bias, which is sort of this kind of game here, right? So imagine this is your world. These are the only things you've seen, and these are the only words you know. Like, this is a triangle, this is a diamond, this is green, this is yellow, this is a ducks. And now if I take you into a new world and I show you these two things, like this red roundish thing and this blue squarish thing, and I ask you which one is the ducks, who thinks it's this guy? Okay. Who thinks it's that guy? Okay, that sort of worked. I think we had a pretty clear majority for that guy. And this is shape bias. Shape bias means that when you hear a word and you see something, your initial assumption is that the word is used to describe the shape of that object. Not the color, not the consistency, not the viscosity, not the weight, it's the shape. Like, humans are massively biased towards shape. And of course, we can do the same kind of experiments with our agent to see what they do. And the nice thing is, because these are machines, you can completely control for these things. So there used to be some research that said, oh, these machines experience shape bias. And actually, we can show that, no, they don't. You can put any bias into these guys that you want. It's purely a function of the training distribution. So if you take an agent and only train it on color words and this duck thingy, this is the agent learning. By the time it's done learning, it will experience massive color bias. If you do the other thing round, it just sees shapes, and this duck thing, then at some point it'll learn to exhibit shape bias. And if you have sort of a more even distribution, then you actually get a slight color bias as opposed to shape bias. And one reason why I think this is quite interesting is because sort of it leads you to think about, what's actually happening in this model that makes it learn language, and sort of what's sort of the way that it processes language and it thinks about it. And so we can actually analyze this a tiny little bit by, going back to the agent and saying, let's blow this whole thing open. So this is image, this is how we process visual information. So instead of just processing that and taking the top output, let's blow this thing apart a little bit and look at the output of each of the layers of this convolutional neural network, concatenate all of these layers, and then let the agent attend over all of the visual information at these different sort of stages of processing to get a better idea for what information it actually uses when it tries to solve these sort of tasks. I've animated this a little bit. So the next slide is about an agent that's just experiencing color words. So this is the agent running around, hopefully, slow video. And you see the different sort of bits of attention at the different levels. So this is sort of the most basic level, the intermediate, and the sort of level of highest abstraction. And this is how the attention is varied across these three things. And you'll see, like when it looks at color words only, it spikes heavily towards the lowest level of processing. And then when you switch it around and look at shape words, that sort of bias goes away. And now the attention is no longer so big on the color side, but much bigger on the higher sides of processing. And again, you can see sort of from the attention here, the color attention is kind of all over the place, the lowest level attention, whereas the higher levels of attention are very focused on the objects themselves. So this is kind of nice because it sort of gives you an intuition of what's going on in these agents and sort of how they manage to sort of take concepts such as color or shape or other information and translate them into things that come out of sort of the different stages of agent processing. So I think in summary, what I wanted to show with all of this is, we can learn to ground language in perception actions. This is not, the end of it, but this is a start. And the nice thing with sort of these kind of virtual environments is that, by learning everything from scratch, we can avoid this fallibility of, human intuition. We don't program anything into the agent according to our own biases and ideas about language to only then confuse the agent later on. As I think I've showed with some of the experiments here, you get these reasonably generalizable representations and transferable knowledge. You can take agents in one setup and throw them quite quickly into something else and get them to adjust to these things. And you can accelerate learning both through auxiliary functions, through pre-training, through the kind of sort of co-training over time. Of course, that's immediately linked to one of the big disadvantages. We need to accelerate learning because learning is so damn slow. And the other thing is also there's a big question around capacity and forgetting. I'm skipping over that because of time, but like when you try to scale this up from vocabulary of X words to 10 times that, at some point the agent does sort of reach limits of its capacity, just because there isn't sort of a ton of modeling power built into it that would allow it to learn infinite vocabulary. But I think so the key takeaway for me is that if we want to understand language learning better, and if we want to figure out how we can get to better language understanding in machines, one thing to do is to try to treat these machines a little bit like humans and test them like humans. Try to see if we can sort of test for the kind of things we test for in human language acquisition in these models and see if that gives us any hints about how we can sort of get faster, get better, and get closer to actual natural language understanding. So that's kind of it, except there's a big elephant in the room, of course. What's the elephant? The elephant is this guy. This guy is what we learned language in for the past 45 minutes. And that's nice, it's 3D, it's first person, it's partially observed, procedural, there's sort of language. But it's not real, right? This is just a Quake engine. And if you think about the real world, this is the real world. It's so much more complex than this sort of one tiny environment in which we can learn one tiny bit of language and do one tiny experiment about language understanding. And I think this is sort of where we are. This is the big question. Like, how can we get to this? Can we go from this to that? Can we learn language here and learn from there, so we can learn language here? In the real world, real imagery, real complexity. No, green apples floating around in space. And this is a practical talk. So this is the forward-looking part. The short answer is, well, we can try, right? So we've actually taken Google Street View and turned this into a reinforcement learning environment. So this gives you the real-world imagery. So you can have your little agent running around in the real world now. And it's sort of kind of the same environment, except now this is a lot more complex than a couple of apples floating around. And so to give you an idea of what this looks like, is you have sort of these sort of parts of the world. We mapped out a good chunk of New York, of Manhattan, a little bit of London, a little bit of Paris. And this gives you sort of these 5 square kilometer wide bits of the world that you can move around in, and then you have the full RL game environment on top of that, so you can put anything into it that you want. We're literally working on open sourcing this right now, so that there's no download link here, but there will be one in 3 to 6 months, hopefully 3. But it's Street View, so there's sort of all sorts of privacy concerns that we need to address before we put this out, as you'll surely understand. And so we've done one task on this already. This was to test, does this work? Can we learn in the real world? Can we ground agents in the real world? Can we do this with reinforcement learning? And so we have a courier task. So this doesn't use language. The task here is that you drop the agent somewhere in a map, and you give it goal coordinates. The goal coordinates are sort of a function of a couple of landmark buildings that you have to memorize. And then the aim is to go from wherever you are to wherever your goal is supposed to be. again with a really simple action space, turn left, turn right, go straight. And the great thing is this guy works. So this is the agent in Paris, sort of starting up here, supposed to get to there. It doesn't have access to the map, so this is just there for visual information. And this is the agent racing around Paris. As you notice, it hasn't figured out street driving rules, all of that stuff. But that wasn't the aim of this thing, I promise you. But yeah, the good thing is so that we can do. And then the question, of course, is, can we also do this with language? The short answer is yes, of course, why not? The long answer is, well, think about how we could do this. Right? We could construct language-based tasks in such an environment using different kinds of information, right? We could look at driving directions, building a task where the agent has to follow driving directions that you pull from some other source. You could look at tourist guidebooks, right? Like take the top 10 for Lisbon, and then get descriptions of the cathedral, and have the agent in Lisbon run around and find the cathedral just based on the textual description of that thing. There's probably all sorts of fun you could have with Wikipedia, and other kind of textual data sources you could put on top of the real world, and then see, can we use this to try to learn grounded language in something that isn't floating apples in space, but the real world. So this is where I'm going to end. The short answer is, I think this should obviously be the next frontier for grounded language learning, and I hope that after this I've convinced all of you that grounded language learning should be the thing that everyone should be working on. If you're interested in doing so, you let me know, and if not, then, well, thank you for your attention and time. And yeah, there were a ton of other people involved in this. That's them.
Thank you very much for the interesting talk. So through your talk, you mentioned spatial reasoning, but to be honest, what I saw was mostly spatial learning. For instance, if you come back to your example, this, old man behind, young woman, or whatever this example is. Mm-hmm. So, by looking there, if we model this problem as a spatial reasoning problem, suppose that we consider woman and man as two objects, and there is a relation there in that your example, which is spatial relation, which is behind or front of. Then if you model it in that way, you would easily, if you apply converse operation, you can easily retrieve this information. You can have 100% match of that. Also, so the question is, okay, let me to continue and then I will pose the question. So also in the visual part, if you also consider that you could use spatial reasoning to also do some space pruning, like suppose that there is that the agent gets awarded if it picks a green box, let's say, yeah. So if this agent sees 3 green boxes at the front of each other in one direction, through composition reasoning or composition relation, it can infer that it can go to pick up all the 3 boxes without need to go around and keep looping. So my question is, have you considered involving such spatial reasoning in your work such that this might enhance the retrieval accuracies and also the learning accuracies? So I'm just wondering have you considered that?
I'm not entirely sure I understood the question, to be honest. So I think sort of to the first comment you made, you're right in the sense that if it's just a setup of woman behind man, man in front of woman, this isn't a terribly difficult thing to solve. So when I talk about spatial reasoning in this context, what I talk about is spatial reasoning in terms of language, so spatial reasoning through language. And like if you look at some of the examples in data, the language is much more complex than just A in front of B, A behind A. And so I think there is spatial reasoning happening there, in the sense that you will have a number of objects, not just two, but say 4 objects in a room, and you get relations between 2 or 3 of them described and have to infer the other things just through that. So I think you do have spatial reasoning there in that sense. The second question was whether we looked at using, like pre-training something with this kind of thing to feed into the labyrinth example. So I think with the examples that I showed here, with the kind of tasks we discussed here, none of them require spatial reasoning in the labyrinth case. So this is much more about just learning objects and sort of learning to ground language from language into these actions in that world. So I think these are sort of slightly parallel things. We do have some other experiments where you require spatial understanding. So there will be experiments, something like pick up the thing that is to the left of that other thing, but not to the right of that third thing. And then so by exclusion, you have to figure out what to pick up. I didn't go into that here now, but I think this is something that would be interesting to revisit to see if you can incorporate the work from the pure spatial reasoning project.
Okay, thank you very much. So I will pass it.
Yeah, I was close to him, so. Can I?
Yeah, go.
Thank you. Thanks for the talk. I wanted to ask a quick question. Did you control for like the need for learning how to navigate? So there are data sets like Clever, you probably know it, that you can reason about images and text, like pretty much similar, what is left of what is behind what, and stuff like that. So it's more supervised, it's obviously supervised learning, and it converges probably much faster. So do we really need the video part in which we navigate? Can't we just have like images and learn the reasoning from them? Like Clever. What's the difference between this and Clever? That's the question.
Between the last one, this guy here?
No, between the artificial one. Clever is also,
okay.
You know Clever, yeah.
Well, I mean, there's a couple of differences, I guess. One is, so I think you do need the action for some of the tasks. And again, this goes back to, I sort of narrowed this down a little bit here, maybe unfortunately so. There are certain tasks that you can only solve by sort of, looking around a particular scene. Maybe the last one where you have sort of 2 different rooms and you have to figure out something next to something that happens to be green. I guess you can do some of these things in Clever, but to a lesser extent. But yeah, I mean, the basic motivation is similar. I think there is something to be said for imbuing agents with the ability to act, just because this allows you to test for different types of behavior and different types of strategies that don't emerge out of something which is sort of like this visual point-and-click style thing, such as Clever. But yeah, no, I mean, these like, yeah, Clever came out, I think, yeah, a while after this, but it's definitely in a pretty similar vein, and I think, yeah, also addresses some of the things that we're looking at here.
Okay, thanks.
Okay, so when we discussed that an agent was trained for a certain number of iterations, and we compare this to, let's say, how often a human hears a certain word, this of course provokes the question, a human has a lot of time between those words to like reconsider what he heard and maybe in an unsupervised way decide what makes sense. Are there some research ideas which address this?
Yeah, so let me go back to this, one of these guys, this guy. So yeah, there's, maybe there's 2 answers to your question. So one is, no matter how much time a human has to think about this, if anything, this makes it even worse, right? That we need sort of 500,000 of these examples. When you look at, there's interesting research by, I think, Emmanuel Dupuis about sort of certain tribes east of India in the Indian Ocean, where children learn language sort of through just a couple of hundred words of child-directed speech, and so tiny, tiny amounts of interaction. So it's definitely something we need to get down. We've been looking at getting this down, and so some of these auxiliary objectives play towards that. So something like reward prediction and the temporal autoencoding. These are offline auxiliaries, so this doesn't have to happen sort of while the agent acts in the world, but this is something that sort of happens based on a replay buffer, so based on the agent having observed things in the world and then sort of revisiting these memories and updating gradients and weights more on that. So this sort of goes into that direction. I mean, there is a fair amount of research in sort of what people call agent dreaming. I think it's a really interesting field, and this is something that's probably worth looking into to see if you can get these numbers down further. And obviously, there's all of this research in sort of one-shot learning and zero-shot learning, which again sort of goes into directions and like how can we deal with fewer examples in order to learn something. So I think maybe a combination of these things.
Hi.
Hi.
In reference to your initial example, I mean, you said old man behind young women, and then you asked a question, what do we as humans, isn't there a fundamental difference between the cognitive processes? Like, we as humans process the entire information in phrases. For me, old man is one entity, and not like we teach our machines, man and old. So the moment we come at the level of words and tokens, we lose that context and that very important information. And I just want to know, because this is something which I've seen in my research, just trying to apply NLP in different areas. That the moment people come at the level of words or tokens, they lose the entire context. And it's very important to work at the level of phrases.
Yeah, absolutely. I mean, at the end of the day, so this example in the experiments in the Gershman-Tenbaum paper, this was all about sort of reasonably straightforward methods of compositionality, right? This was sort of these recurrent autoencoders, matrix vector recurrent neural network style operations. And if you show this example to say linguists who started their career 10 years before mine, they'll be like, well, you're being ridiculously silly. This is super easy, right? You learn a proper pass tree over that, maybe sort of do a CCG parse, and then based on information on top, we can actually identify sort of the similarity of these things and the equivalences between sort of this, object-subject reversal. So there's definitely linguistics ways to analyze this that would lead you to the right conclusion, semantically speaking. I think the point I was trying to make is that when we think about natural language understanding, the big problem is sort of all of that sort of linguistic research back then, it didn't lead to natural language understanding, right? It led to things like the English resource language, which is hundreds of thousands of rules that try to go from syntax to meaning and never quite got there. So there are ways to do this, but they will fall short for other reasons. I'm not saying sticking these things into an LSTM is the way that we're going to solve this. I think not. Probably you want to look at some combination of sort of neural continuous approaches with some degree of linguistic information, with parse information and whatnot. There's interesting research by a colleague of mine, Chris Dyer, on recurrent neural network grammars that he's probably going to talk about on Wednesday here anyway. There are ways to do this, and I think that would be interesting. And yes, those ways may be closer to how humans process data.
So I had a question about the Street View data set. So it seemed like the performance on that was pretty amazing. But is it more like, has it learned actual useful features about navigating around London, or is it just maybe picking up random artifacts from the street or something like could you possibly, if Street View data is kind of collected once a year again, right? If you kind of trained on 2017 data and used it on 2018 Street View, would that still work, or
Yeah.
Okay.
I'm not 100% sure if this is in the paper I was referencing here, but we've run some experiments on exactly that kind of setup. So taking Street View data from the past and more recently and seeing how the transfer works. Also again, so details I skipped over, but in the paper. So most of the agent work in there was on building agents that can easily transfer from one city to the other. And I think that's sort of, again, one of these ways you can analyze these agents, and what they learn is how easy is it to take a trained agent in one city, say London, and then have the same agent work in Paris. Like, does that take the same amount of time of training? Then it's probably just random artifacts. Is it super quick, and it just takes a couple of iterations until it's sort of figured out where the main landmarks are that we use to reference goals? Then it's probably something more sensible. So it does seem to be that we learn reasonably sensible things there.
Okay, thanks.
Okay. I have kind of philosophical question.
Okay.
It could be strange, but I'm actually very curious. So the original question sounds like what is your motivation on work on this problem in general? Can be a bit more specific question, like how you see the future of this kind of applications, like, or in general, artificial intelligence. So,
sure. God. So, no, I think the honest. There's sort of two parts to this, right? I mean, the honest answer of I think most computer scientists ever is like, what's your motivation for doing your work? It's inherent laziness, right? We all became computer scientists because of laziness and because we try to automate things that we don't want to do manually every single time. If we can get to natural language understanding, if we can get machines to understand natural language, we can get those machines to do things for us. That's kind of really useful.
Yeah. What are those? What could be those things? What you think about them? Like what you imagine?
Oh, I don't know. I mean, Alexa, order a cup of coffee. That sort of thing.
Is it too personal?
No, it's not too personal. It's more something that I find it. I always think it's a bit difficult to sort of partition Mars before we manage to land on it. And I think there are a lot of interesting applications that would come out of this kind of technology. The obvious starting point is, of course, anything related to people with disability. I read about a startup the other week, which is sort of this thing where, as a blind person, you can press a button on your phone, and then the app loads up, and someone else in the world will sort of get a video feed from your phone, and will describe to you what's happening. The idea is sort of to make things more accessible to blind people, so that they can be there. And I don't know. The example was like the birth of a child, which I'm not sure if you want to have described, but there will be other things that you want to have described. And if you can automate that kind of stuff, that would be pretty cool. So maybe that's a starting point.
Okay, thank you very much.
I'm wondering on this paper, what is the reward? Is it just to go to the points, or you have a more complex reward? For example, if you wait at traffic lights, or no? Okay, but maybe it's possible.
Have you seen the guy? This guy doesn't stop at traffic lights. Okay. No, so the reward is reasonably simple. The most basic reward is just there's a goal location that we sort of give you these coordinates to. You get the reward. We tried a couple of auxiliary rewards because this is obviously like a super sparse signal. So we tried some rewards where you sort of just randomly place rewards all over the map to sort of encourage exploration in the beginning. We tried some other rewards where, like, instead of just having the goal, you sort of have this reward cone over it. So the closer you get, the more incremental reward you get. That sort of helped to speed up training, but in the end it wasn't necessary, so we got rid of it again. I think, like this agent, that video, that's just where you have to reward for where you have to go.
Okay. Thank you.
Hey, thanks for the amazing talk. I'm here. Nice talk. I enjoyed it a lot. Is it turned up? Hello. I have two questions. From how I understood this is that you're trying to ground the language because you're trying to ground the language in vision because whatever encoding of language you're doing, just with language, is insufficient to, in order, for example, in your case with this woman and man example, to in order infer the correct information that you need. Now my question being is, well, additionally what you could do is, I mean, you could incorporate multiple tasks. You mentioned it before, zero-shot learning, few-shot learning. So if you have a model that already knows about paraphrases, or if you have a model that knows about entailment, you know, I think with entailment we could already go a very long way with that. That's like one way. And what I was trying to ask is, do you think future research is going to be more directed towards fixing this kind of structural bias in which the model is kind of incapable of encoding whatever we need to know? Or do you think the future work is going to be more directed towards taking information from whatever, like grounding languages in vision or grounding languages in knowledge bases? Because all those separate knowledge sources, they have their own limitations themselves. So what is your kind of gut feeling? Where is it heading towards?
I don't know. I'm sort of a broad church researcher, I think. I think both things are perfectly plausible research directions. And you know, of course, this talk was very consciously biased to my own research. But there's a lot of other research in grounded language learning these days. There's been interesting research by a bunch of teams with sort of looking at similar environments, looking at similar kind of problems. And I think we'll find research going in both directions. So there's been some take-up from people in sort of cognitive science and sort of, you know, the proper linguists and sort of language acquisition work, whom we've started talking to. And I think for them this is sort of an interesting way to see, can we test sort of, you know, the theories about human language acquisition in these machines, and is there something we can learn about human language acquisition by studying machinery as well? So I think this is sort of one interesting research dimension. I mean, as I sort of said myself, I think, well, what I'm most interested in right now is sort of, can we go from sort of the abstract kind of toys things to language grounding in a more plausible way? So, you know, getting away from sort of these artificial game worlds, can we get away from artificial language, so like sort of simple scripted things, to something that is, you know, natural language, noisy language, natural world, noisy world. And yeah, there will be other people who are looking at, you know, more complex tasks. And I think that there's some work on language grounding in Minecraft. And of course, you know, this is, you know, build me a house is much more complex than pick up a green banana. So, you know, all of these things.
Okay, thank you very much.
No. The question disappeared.
Can I ask a very quick question while they're looking for whoever wants to answer? So thank you very much for your talk. It was very interesting. I have a little bit of question about another maybe point of development of the game. So what do you think about multiple agents within the game that try to interact in some way? Maybe like a task that requires both of them cooperating in some way? Because, well, this is something some part of human learning as well. It's like we don't do things alone, we do them socially.
Yeah. This feels like a trick question. So it's a bit complicated. I think that there's two answers to this. One is sort of the question of, do we want to learn to, like, do we want to try to do grounded language learning in the context of multi-agent situations, where the multiple agents could all be learners, or it could be learners and humans? Yes, definitely. I think this would be really interesting. And again, there's been some work on this. I think like Facebook Research had this paper on learning by Amazon Turk Descent or something like that it was called, which was sort of this idea of like a little role-playing game where you have, you know, Amazon Turkers play against computers and sort of mutually learn over time. I think this is really interesting. I really struggle to find good ways of making this happen because like whenever I ask, my boss says no about me hiring 500 people to sit in a room and play with computers all day. The second part why I said this is a slightly loaded question is sort of, all of this research, there's research on emergent language. And so there's a lot of that also in the context of multi-agent setups where you have multiple agents playing together in a collaborative game or competitive game, and they have to communicate via language. So personally, I think this is really different, and I think this is interesting for multi-agent research. It's interesting for sort of game theory research and trying to figure out how we can imbue agents with game theoretic elements. I think it has nothing to do with language learning whatsoever, because just by virtue of these setups, what you will learn is protocols. You won't learn language. And the nice thing about human language is all of the messiness and all of the evolution that led us to coming to this language. And if you try to do this in sort of an emergent language setup, you'll just have sort of this rat race of trying to build better models, trying to build more complex worlds that force you to learn more complex language and vice versa. And like personally, I don't think that's a super promising route to get to natural language understanding.
I had a sort of interesting comment or an insight that I had. So regarding accelerating the learning, you said that a model which had some kind of information in advance learned much faster. So I was wondering, would it be helpful if the model had access to some kind of an oracle to which it could ask queries to speed up learning, relating it to the other example that you gave about shapes, for example, that there is an inherent bias to shape. Yeah. So the model could ask whether shape is an important information to focus on, and then you guide it.
We actually tried something along those lines. So we tried to build agents that would sort of get to ask questions while they solve a task. Based on that, sort of get a bit of extra information. We haven't gotten particularly far with this yet, because I think this is kind of the thing where you take a sort of medium hard problem and you try to make it easier by adding a really hard problem on top of it. Because now we have an agent that not only has to learn, what does it mean for something to be green or to be ladder shaped, but also how do I ask about all of these things? And I think the latter thing is actually more complex. So I think if someone found a good way of getting this work, this would be really cool. And I'd love to see that work, but I tried and we didn't get very far with it.
Great, thank you.
Okay, so I guess it's time to finish. Karl is going to be around, so if you feel free to talk with him offline. Thanks a lot again for the talk. Let's thank the speaker again.
Thank you.